So we're going to discuss about Vant Hoff factor. To understand Vant Hoff factor, we need to understand the certain characters of a solute. So when we take a solute and add them in a solvent, okay, so when we take the solvent, okay, in this solvent, if we add the solute, there are certain things which will happen with the solute. In one case scenario, the solute may break, okay, or it may not break, okay, it doesn't break, or join, we can say. In the third case, it may possibly join, okay. If it breaks, we call it as, we'll say that the solute has got dissociated, so that means there is dissociation. But if it joins, we'll call it as association, okay. Now there is again another thing that we have to consider. When the solute is breaking, how much of this solute, okay, how much of this solute, let's say if you had taken 10 solutes or 10 mole of the solutes, in 10 mole of the solute, how many of them has broken? Let's say out of 10, 3 has broken, or out of 10, all 10 has broken, okay. Or we took 10, okay, these 10 molecules, they got associated as pairs, okay, they got associated as pairs, so we had 5 molecules after association. So another thing is, there may be partial association or there may be complete association. Partial association means, let's say we had 10 molecules, out of that 4 of them has paired up, okay, so 4 of them has paired up, so we have now 2 pairs. But the rest of the 6 molecules, okay, the rest of the 6 molecules didn't pair up, okay. So we can see that out of the 10 molecules, out of the total of 10 molecules, only 4 of them has got pair up, but rest 6 of them didn't pair up, okay. So this is partial association. Now complete association would have been, we had 10 molecules like this, and in that case, if all of them would have paired up, then we would have got 5 pairs like this, okay. So when we are adding the solute in a suitable solvent, we need to consider these 3 scenarios, whether they are breaking, or whether they are joining, or if it doesn't break or join at all, okay. So these 3 scenarios has to be considered. And when they are breaking, whether they break partially, okay, or they are breaking completely. And then generally in the association we had partial association, okay. So to understand the association or dissociation, Vant Hoff studied that part or that nature of the solute for the first time, okay. That was somewhere at the end of the 18th century. So he studied that the particles that was added as solute, after adding them in the solution, whether the number of that particle has remained the same, whether it has increased or whether it has decreased. So this is before dissolving, and this is after dissolving, okay. So what he has done was, basically he was comparing the number of particles after association or dissociation. Okay, he was comparing the events, okay, over the number of particles before dissociation or association. Okay, so it's a very simple phenomenon. Now if we look at this case, let's say if we take a substance, let's say we have taken a solute which dissociates into two particles. Let's say, for example, the solute is sodium chloride. Okay, sodium chloride in the solution will dissociate into sodium ion and chloride ion. So if we would have taken 10 mole of the sodium chloride in the solution when we add them, assuming that the sodium chloride is a strong electrolyte, every 10 molecule or the 10 mole of the sodium chloride that we have taken, every one of them will break apart into the sodium ion and the chloride ion. So each sodium chloride will give us 1 mole of sodium ion and chloride ion, 1 mole each of sodium ion and chloride ion. So now what we have is, that means in total we can have 2 moles in total. So 1 mole of sodium ion and 1 mole of chloride ion from 1 single mole of sodium chloride. Okay, so if we had taken 10 mole of sodium chloride, that means we'll have 10 mole of sodium ion and 10 mole of chloride ion. So together this is before dissociation, and after dissociation the total number of ions that we have, that is 20. So that is after dissociation. Okay, so Vant Hoff, what he did, he produced a formula which compared the number of particles after dissociation, so by before dissociation. So after dissociation it is 20 and before dissociation it is 10. Okay, so if we just compare it, what we see is we are getting a number, the ratio. So that means the number that you're getting, that is technically the term that represents by how many times has the number of the particles increased after adding it in the solution. Let's say we had 10 mole of sodium chloride, and if we increase it by 2 times, that means the concentration now is, if we increase it by 2 times, the concentration would be 20 mole. So let's imagine if the solution is for 1 liter, then we could have said that it is 20 molar. Okay, so whatever be the case, so what we can understand is the Vant Hoff factor, if it is 2, that means the concentration would increase by 2 times, and if the Vant Hoff factor is 3, the concentration, that means after adding them in the soluble solvent, their concentration would increase by 3 times, and if it is 10, then it would increase by 10 times, like that. If we take some more examples, let's say if we have barium chloride, it will dissociate and break into 1 time barium and 2 times chloride. So which means if we had 1 molar barium chloride, okay, we'll have 1 mole or 1 molar barium ion and 2 molar chloride ion. So assuming that they have dissociated completely, so the Vant Hoff factor in this case it would be the number of particles after dissociation. So after dissociation it is 3 and before dissociation it is 1. So the Vant Hoff factor that we are getting is 3. So if we are getting it as 3, it means the concentrations of the solution has increased by 3 times. Okay, so if we have other if we take some other complex ions, or as an example, let's say potassium hexacyanoferrate, what we can see is it will give us 4 potassium ion and then 1 hexacyanoferrate ion with this 4 minus charge. So what we can have is, if we would have taken 1 molar of this potassium hexacyanoferrate, we can have 4 molar concentrations of potassium ion and 1 molar concentrations of hexacyanoferrate ion. So what we have also assumed is there is complete dissociation. So now if we consider the Vant Hoff factor, the number of particles after dissociation it is 5. After dissociation it is 5 and before dissociation it is 1. So it is 5 over 1. So that means the Vant Hoff factor is 5. So if our Vant Hoff factor is 5, which would mean our concentration has increased. Our concentration has increased by 5 times. Okay, so I hope it is clear. Now, how the understanding of the concentration is going to be important to us. We understand that the qualitative property, the qualitative property, in short if we write it as Cp, the qualitative property is directly related with the concentration. Okay, so which means if the concentration increases by 2 times, the qualitative property should also increase by 2 times. If the concentration is halved, then the qualitative property should also be halved. Okay, normally the concentration increases if there is dissociation. The fourth qualitative property that we have is the lowering of vapor pressure, that is represented by, let's say for A, let's say we take the solute as A and the solvent as B, okay, to get our solution. So now assuming that the solute is non-volatile, that means which doesn't give vapor. Okay, so considering that A is non-volatile, if we add this non-volatile solute in a volatile solvent, the formula that we had for the relative lowering of vapor pressure is something like this. This equals to the mole fraction of the non-volatile solute. So what we understand is The other colligative property that we have is the elevation of boiling point, that is represented by del Tb, which equals to Kv into molality. And then we have the depression of freezing point, which is equal to the K of F, that is molar freezing point depression constant, multiplied by molality. And then the fourth colligative property that we have is the osmotic pressure, so which is equal to the concentration in terms of molarity multiplied by the universal gas constant, and then which would be again multiplied by temperature. So this colligative properties that we have out here, the depression of freezing point, the depression of vapor pressure, your elevation of boiling point, the depression of freezing point, and the increase of osmotic pressure, all of these are dependent on the concentration. Okay, they are directly dependent on concentration, which means they are directly related with concentration. So if we increase the concentration by 2 times, the colligative property would increase by 2 times. If you decrease the concentration by 2 times, the colligative property will also decrease by 2 times. Okay, now after understanding the Vant Hoff factor, what we understand is, depending on the type of the solute that we have considered, okay, so let's assume that if there is a dissociation, okay, and the Vant Hoff factor is 2, in that case this colligative property will increase by a factor of 2. Okay, so what we understand is, whatever is the colligative property, that colligative property would increase by the factor of Vant Hoff. Okay, so by the factor of Vant Hoff, what we mean is, like we have discussed earlier, that if the Vant Hoff factor is 5, the concentration increases by 5 times. If the Vant Hoff factor is 3, the concentration increases by 3 times. And what we understand is, since the colligative property is directly proportional to the concentration, okay, so as many times the concentration increases, the colligative property would also increase by that many times. Okay, so we can multiply this concentration with the Vant Hoff factor. Okay, so what we have is, you'll have the relationship like this everywhere, okay, because the concentration is increased by the Vant Hoff factor. Now what we can observe from this relationship, okay, from all this relationship, what we can observe is the colligative properties like the lowering of vapor pressure, the elevation of boiling point, the depression of freezing point, the osmotic pressure, all of them increases by the factor of Vant Hoff, okay, that is represented by I. Now what does it mean? It means that, let's say if we have a solution which was supposed to boil, okay, after adding, let's say, a salt in a solvent, after adding a salt in a solvent, the solution, let's say, was supposed to boil at 100 degrees Celsius, okay, but what did we see? It didn't boil at 100 degrees Celsius, but rather it boiled at much higher temperature. So let's say it boiled at 200 degrees Celsius. Okay, so then what we can do is the Vant Hoff factor, okay, by comparing these values, it was supposed to boil at 100 degrees Celsius, but it boiled at 200 degrees Celsius. So in that case, the Vant Hoff factor I would be equal to 2. So if you're getting it as Vant Hoff factor I equals to 2, it means, what does it mean? It means that the concentration has increased by 2 times. So this salt that we have added, what would it indicate? It has broken apart into 2 entities. Okay, it has got dissociated into 2 particles. Now imagine if it would have boiled at 300 degrees Celsius. You were expecting a temperature of 100, but you got it as 300. So in that case, the Vant Hoff factor I is equal to 3, which means the concentration has been increased by 3 times. So if you add 1 molar of the salt in the solvent, then you will get technically 3 molar in the solution. Okay, so by comparing this values, the theoretical values that we were expecting and the experimental values that we are getting, we can also estimate the Vant Hoff factor, which would be an indicator about the number of times the concentration has changed in a solution after your association or dissociation, which means we can have another formula for Vant Hoff factor. So the Vant Hoff factor I would be equal to the observed colligative property over your theoretical or normal colligative property. Okay, this observed colligative property, the experimental, or we can say the experiment which was under observation, so we can say this is observed value, or since the value that we are getting out here is abnormal, so we can also say that in some cases as abnormal value, but as of now we'll just go by this. So this observed, in some book you might also get it as experimental, experimental colligative property. Okay, so it is observed or experimental colligative property over your theoretical or normal colligative property. So based on this simple comparison, we can also get the value of Vant Hoff. Now regarding the Vant Hoff, there is another thing that we need to consider: the colligative properties. Okay, so we have 4 colligative properties, so let's write it again. Okay, these are the 4 colligative properties that we have. So this is 1, 2, del Tf equals to Kf into molality, and then we have your del Tb equals to Kb into molality, and then we have your osmotic pressure pi equals to CmRT, okay. So if we expand this concentration part, we better also write the Vant Hoff factor I. Okay, so if we just look into the concentration part of the formula, okay, what we see is the mole fraction. Let's write the mole fraction part directly instead. So the mole fraction part, that is the number of moles out of the total moles, okay, out of the total moles. So multiplied by I, number of moles of A, let's say the solute, is weight of A over the molecular mass of A. So let's just keep it as number of moles of the solution. multiplied by I. So this is Kf. Molality is again number of moles of the solute by weight of the solvent in kg. So multiplied by I. So this is Kf equals into number of moles would be again weight by molecular mass. This is the weight of the solvent in kg multiplied by Vant Hoff factor. This is Kb into again the number of moles of the solute by weight of solvent in kg multiplied by Vant Hoff factor. So this is Kb into your total moles of the solution in kg multiplied by Vant Hoff factor. Concentration in terms of molarity is the number of moles of the solute that is present in 1 liter of the solution. So we have the formula like this. Now the number of moles formula is the weight by molecular mass. So this is volume in liter, so this is R into T into I. So a very important point that we can observe out here is that the qualitative properties, the qualitative property is inversely related with the molecular mass of the solute that we are taking. This is one important observation that we can consider. It is inversely proportional or inversely related with the molecular mass. So qualitative property is inversely proportional with the molecular mass of solute. Now other thing that we also know is since we are already going to be familiar with the Kf, Kb, the R or the temperature conditions that we are going to use for our experiment, and then most importantly if we are taking any unknown sample, so that sample would be our solute. So that unknown sample, it may be some toxins or it may be some kind of substance that you want to analyze. Let's say you want to consider the type of the chemical molecule which is there in some kind of flowers or fruits, or some of the things that you are supposed to consume in your diet. So any sample, it may be some solute particles from outer space. So any kind of sample, if we want to find this molecular mass, we can take the help of the qualitative property. So by taking the help of the qualitative properties, we can easily estimate the molecular mass of the unknown sample. That is a very important utility of qualitative property. It can be possibly asked in exam, what is the use of qualitative property? It is used to estimate molecular mass of unknown sample. So that is the use of qualitative property. Now when we are trying to estimate the molecular mass, we need to understand the relationship between the qualitative property and the molecular mass. And what did we observe? We observed that the qualitative property is inversely related with the molecular mass of the solute. Solute means the sample that we are considering. So now let's say we have found the molecular mass of a sample. So if we use the qualitative property to estimate the molecular mass of the unknown sample, let's say we were expecting the molecular mass to be 4D, and we got it as AD. So in that case, our Vant Hoff factor would be 2. So now what can we say? we can see that again the concentration has increased by how many times? By 2 times. Okay, so based on that we can write another formula of Vant Hoff factor, which is the normal molar mass of solute over your observed molar mass of solute. Okay, so now coming back to the earliest discussion that we had regarding how many of the particles would associate or dissociate. So we have to, in that case, we have to consider the degree of dissociation. So let's consider the degree of dissociation. Or in this case it may be association as well. Okay, for our simple understanding for now, let's just consider only the dissociation part. Okay, so now what we have is, what does degree of dissociation or alpha means? The degree of dissociation or alpha would mean out of the total molecules that you have taken. Okay, let's say we have taken 10 molecules, and out of those 10 molecules 2 has got broken apart. So that means our degree of dissociation is 0.2. Okay, so let's say if somebody would have given us the degree of dissociation alpha as 3, 0.3. In that case, what would it mean? It would mean that out of the 10 molecules that we have taken, 3 has been broken apart. Okay, so let's say we had 10 molecules, and after adding them in a solvent to prepare the solution, what has happened? 3 of them, this 3 of them has broken apart, but the rest 7 of them didn't break. Rest 7 of them didn't break. So our alpha, that is the degree of dissociation, in that case would be out of the 10 molecules only 3 has got broken. So our alpha value, that is the degree of dissociation, would be 0.3. Okay, so what we had before dissociation, we had 10 molecules. Okay, after the dissociation, what we have got 7. Okay, we have got 7. So how many has got broken? 3 has got broken. Earlier, like before adding, none of them has broken, so the number of particles that got dissociated was 0. But after adding them in a solvent, this is before dissociation and this is after dissociation. Okay, so what we see is we have taken 10 molecules of the solute, and after adding them in a solvent, 3 of them has broken apart. So when we break into 3 molecules, let's say they are breaking into 2 parts each. Okay, so the total molecules that we have is 3 times 2. Okay, so total molecules that we have on the product side is 6. And what is the amount of the solute which is undissociated? The undissociated part is 7. So in that case, if we would have said it for the alpha, okay, for the alpha it is out of the 10, 3 has got dissociated. But if we consider the Vant Hoff factor I, the one that we discussed just a while ago, what it considers is, it considers the ratio of the number of particles after dissociation by number of particles before dissociation. Okay, so in that respect, what we see is the number of particles before dissociation, that is 7 and 6 together, it is 13, and then the number of particles before dissociation was 10. Okay, so in a way we can say 10 plus 0 or just simply 10, so that is equal to 10. So what can we understand for the Vant Hoff factor? That is I equal to 1.3, which means the concentration, okay, the concentration has increased by how many times? By 1.3 times. You should always remember that the Vant Hoff factor is nothing but by how many times has the concentration increased or decreased. Okay, so we need to, whatever value that we are getting, if we are getting it as 1, that means the concentration has remained the same. If we are getting the Vant Hoff factor as 2, that means the concentration has increased by 2 times. Okay, and if we are getting it as 1.3, then the concentration has changed or increased by 1.3 times. If we are getting it as half, then the Vant Hoff factor, or I mean the concentration has changed by 1 by 2 times, which means the concentration has been decreased. Okay, so now we can generalize this scenario. Okay, if we just try to generalize this scenario, what we can have is, let's say we have AXBY solute which will dissociate to give us, okay, A would be the cation by default, so what we can have is, this should be X times A Y plus and your Y times B X minus. Okay, so if we take C molar concentrations of the solute of AXBY, okay, then what we can have is, assuming that this is a weak electrolyte, okay, we should understand that the weak electrolyte, in the weak electrolyte there is no complete dissociation, there is partial dissociation. So the weak electrolyte, it will dissociate partially. So if it dissociates partially, some of the electrolytes will be left out. Some of the electrolytes will be left out undissociated. Okay, so which will be left out undissociated. So what we understand is the degree of dissociation. If we look on the other part, if we just consider the degree of dissociation on the other side, let's just take it as alpha. The degree of dissociation is the number of the ions, okay, which are being formed out of the total concentration, okay, which means the ion concentration would be equal to, since for the AXBY solute we are taking the concentration as C, so it would be C alpha. Okay, similarly we can see that for the B, it would be C alpha as well. Okay, so what we have is, we have C alpha for the cation, but what we also see is this cation is X times, so that means we are going to multiply this C alpha with X. Okay, and similarly like that for the anion, we would also have Y times the C alpha. Okay, so now the number of particles which will be left undissociated, it would be C minus C alpha. Okay, that is the number of the particles which have got undissociated. Now, in case if you're wondering how did we get it as C minus C alpha or X times C alpha, in that case we can try eating some biscuits. Okay, let's have some special cookies. Okay, so let's say we have some cookies. Okay, let's take 5 cookies, and we are going to break 2 of them. Okay, so if we break 2 of them, what we can have is, if we break 2 of them into equal parts, so if we break 2 of them into equal parts, what is the number of the biscuits that we would be getting? If we just break just 2 of them, okay, we'll get 4, isn't it? So we have started with 5 cookies, and out of those 5 we have taken 2 and we have broken them into 2 parts each. So the number that we are getting is 4, the number of the cookies, okay, after breaking them apart. And what is the number that is left? 3. So instead of the 4, what could we have written? We could have written it like this. This is 2 times 2, okay, because we have taken 2 biscuits and we have broken them into 2 parts, okay. But the number of cookies that is left unbroken is 5 minus 2, okay. Exactly like that, instead of the 5, let's say we took C molar concentrations of the solute, and here the degree of dissociation in the cookie example was, out of the 5, out of the total, okay, out of the total 5, 2 was broken, okay. So this 2, it would have been 5 times alpha, okay. Here instead of the 5, what we have got the C, okay, and instead of the 2, okay, this is 2 times 2, so instead of the 2, okay, what we have is, we have the ions, okay. So we have the ions which was breaking apart. So this ion concentration that we can have is C alpha, okay. So we have the C alpha. So if we consider the 5 as the concentration, then 2 in this case would be 5 alpha. So instead of writing it as 5, since for the 5 we have already taken it as C representation, so this would be C minus C alpha, okay. So from this total concentration of C, we have subtracted the C alpha, which means this is the part which is forming as the product. So instead of this, what can we write? We can write it as C alpha, okay. So now if we come back to our point over here, what we can understand is the Vant Hoff factor. If we take it, it should be the number of particles that is present after dissociation. So that is, after dissociation is C minus C alpha plus X times C alpha plus Y times C alpha divided by the initial concentration, okay. The total initial concentration that we have is C0 times the cation and 0 times the anion, so together it would be C molar concentrations. Now if we take the C as a common factor, we could have 1 minus alpha plus x of alpha plus y of alpha divided by c. So CC would get cancelled out. So what we can have is, we can have I equals to 1 minus alpha. Now if we take the alpha in the other part, in these two parts, okay, if we take the alpha as a common factor, then we can have x and y. Inside the bracket, let's close the bracket. So this x and y, it represents the total number of the cations and the anions which are formed. That means the number of the particles which are being formed from a given molecule of a salt or a solute. Okay, the number of particles that would be equal to x plus y. Okay, so that means here in place of x plus y, we can have I equals to, in place of x plus y, what can we write? We can write n. Okay, so this would be n alpha. So if we simplify or evaluate further, then we can take the I on this side. So this is 1 minus I, and this would be alpha minus n of alpha, and what we can have is, we can take out the alpha as a common factor, so this will be 1 minus n, 1 minus I. So alpha would be equal to 1 minus I over 1 minus n, or we could have also written like this: alpha equals to I minus 1 over your n minus 1. Okay, so this expression is the expression that relates the degree of dissociation, the number of particles which are being formed, and the Vant Hoff factor, which represents the number of times the concentration has increased. And remember, this relationship is for dissociation. Okay, but if we consider the association, and another thing that you should remember is, in the board exam they would possibly ask you to derive this part. Okay, so the relationship between the degree of dissociation, the Vant Hoff factor, and the number of particles. And if it is medical entrance exams or JEE, then they would possibly ask you which one is the correct representation for the degree of dissociation. Okay, so they will give you some forms like this. Okay, one of this form would be the correct form. Let's say one of this form is like this, and there would be other forms like, let's say, n equals to I minus 1, alpha minus 1, which may look very much similar and may confuse us, so we need to be careful with this. So by looking at the correct form and by remembering it, in case if you forget it, you can derive it very easily and you can come up with your answer. Now let's consider the association. So you should know that when the number of particles, okay, let's say when two number of particles associates with each other, we call it as dimer. So if it associates, their concentration, or if it dimerizes, their concentration would become half. And similarly like that, if three molecules associates, then we call it as trimer, and their concentration would decrease by 1/3. And if four molecules associates with each other, then we call it as tetramer, and exactly like the earlier case, their concentration would also decrease by 1/4. But that would also again depend on how many of them are associating. Okay, so when we say that their concentration has become half, it means all of them has formed a dimer. Okay, but remember that in very rare occasions only, okay, it can happen, but in normal case none of them will associate completely, only some of them will associate. Okay, so in that case we can consider the degree of association. So the degree of, just like the degree of dissociation, we can have degree of association. Okay, so let's say if the degree of dissociation is, or sorry, I mean if the degree of association is 30%, okay, so that means out of the 100 molecules 30 has got associated. Okay, or if the degree of dissociation is degree of association is 0.2, it means out of the 10 molecules 2 have got associated. Okay, so regarding the association, if we take some examples like the earlier case, let's say we have 10 cookies. Okay, 1 2 3 4 5 6 7 8 9 10. Okay, we have 10 cookies, and what have we done? We have attached 2 cookies. Okay, we have attached 2 cookies. So earlier we had 10 cookies and we have dimerized 2 cookies. So if we dimerize those 2 cookies, the number of the cookies which didn't dimerize or which didn't associate is 10 minus it would be 10 minus 4. Okay, so it is 10 minus 4 because we had 10 and 6 will be left. Okay, so now what we see over here is instead of the 4 we should have, on the right hand side, we should have had this number. Okay, so the number of cookies that has got dimerized, if we count it as numbers, okay, we are getting 2 cookies like that, but in reality how many cookies have we taken? We have taken 4. So if we take this as C, 10 molar, okay, let's take the concentration as C for the 10 molar. So what we understand is, let's say it is 10 minus, or for the 10 we have the C, so we can write it as C minus C alpha, and here since the concentration, so for the 4 if we write it as C alpha, what did we observe earlier? We observed that the 4 was divided by 2, so the C alpha we are going to divide it by 2. Now if it is a dimerization, okay, we are going to divide it by 2 at this part. Okay, if it is a trimerization, then we are going to divide it by 3. Okay, so accordingly what can we write? We can write, or we can generalize, okay, for this expression. If we generalize it for this expression, let's say we had n number of A which has got associated n times, so what can we write? This is before association, the solute is C and the product is 0, and this is after association. What we can have is, this would be C minus C alpha, this is C alpha. So since they are associating by n times, so it will reduce by how many times? By n times as well. Okay, their concentration would decrease by n times. So now if we analyze the number of particles, or compare the number of particles about after this association by before association, that is the Vant Hoff factor. Okay, the number of particles after association, okay, by the number of particles before association. So what can we write is, we can write before association it is just C, and after association it is C minus C alpha plus C alpha by N, which means if we take the C as a common factor, we would have 1 minus alpha plus alpha by N divided by C. Okay, we can cancel out this too, so that means we are going to get the relationship I equals to 1 minus alpha plus alpha by N. So by looking at this expression, we can clearly establish the relationship between the Vant Hoff factor, that means the concentration that has changed after the association, and the alpha, that is representing the degree of association, and N, that is the number of particles which are associating. Okay, so I hope it's clear with everyone, and there is just some small points that we need to also consider regarding the degree of dissociation and the Vant Hoff factor. Let's look into this. We should always remember that regarding the degree of dissociation, okay, regarding the degree of dissociation, that is alpha, that is degree of dissociation, is, like I have told you earlier, the number of the particles, okay, the number of the particles which has dissociated, or associated, we can say, out of the total, okay, out of the total particles or the molecules that you have taken. Okay, so what we have is, let's say we took 10 particles, like I told you earlier, we have taken 10 particles, and out of them 3 has broken apart. So our degree of association in this case, it would be 0.3. Okay, so now that means the maximum that we can have, okay, we took 10 and the maximum that can break is 10. Okay, by taking 10 molecules we cannot break 11 molecules. Okay, so you should always know that the degree of dissociation equals to 1. That is the maximum possible value for alpha. It can never be more than 1. Okay, since it represents a fraction or a ratio, so this value can never be more than 1. Okay, and when we are saying that it is 1, it means whatever molecules that you have taken, if you have taken 10 molecules, 10 has got broken down. If you would have taken 50 molecules, 50 molecules has got broken down. That means every molecule that you are going to take, every one of them will break. Okay, and that is a character of a strong electrolyte. Okay, so in the strong electrolyte there is 100% dissociation. Okay, but there are electrolytes which dissociates but not completely. Okay, so let's say here in this example that we have considered, we have taken 10 molecules, but out of those 10 molecules, all of them didn't break, only 3 of them has broken apart. Okay, so very few molecules has got broken, so in that case we'll call it as weak electrolyte. Okay, and what we can see is the value of alpha is 0.3. This is less than 1. So for the weak electrolyte, the value of alpha, that is degree of dissociation, or degree of dissociation, would be less than 1. Okay, for the weak electrolyte, this character has to be remembered about alpha. In any exam, this is generally asked, and we need to take care of it. And for the strong electrolyte, the degree of dissociation, that is alpha, is equal to 1. Okay, it's a very important point. And if we go into the Vant Hoff factor, what we can see is, that let's say Vant Hoff factor is all about the number of particles after dissociation or association by number of particles before dissociation or association, let's say. So what we can have is, let's say we can have 3 scenarios. We had taken 10 molar concentrations of the solute, and we still have 10. Okay, so that means here in this case we'll get the Vant Hoff factor as 1. So if you are getting the Vant Hoff factor as 1, it means the concentration didn't change. Okay, so if the concentration doesn't change, that means it is a non-electrolyte. Okay, it didn't break. But let's imagine or consider a scenario where you took 10 molecules, and after dissociation they broke apart and they formed 20 molecules, or their concentration has increased by how many times? By 2 times. Okay, so here I equals to, the Vant Hoff factor is equal to 2, which is greater than 1. Okay, so if the Vant Hoff factor is greater than 1, that means the concentration has increased. It has increased by how many times? By 2 times. Okay, it has increased by 2 times. So the increase in concentration is because of the association, because of the dissociation. So for the dissociation, the Vant Hoff factor is always greater than 1. Okay, like that we can have another scenario where the Vant Hoff factor, if we take the ratio, we had taken 10 molecules, but these molecules, they have got associated. Let's say they have formed a dimer and they have produced, if it dimerizes, two molecules will get attached with each other, so in total we will have 5 out of 10. So which means the Vant Hoff factor would be equal to half. So here we can see that the concentration has been halved. Okay, that is I is equal to 0.5, which is less than 1. Okay, so the concentration, if it is less than 1, it means the Vant Hoff factor, if it is less than 1, it means the concentration has decreased. And why did the concentration decrease? Because of association. Okay, so this kind of small relationships that we can see out here, they are generally being asked in the exam. Okay, so we need to be very careful. Now the other thing, let's consider some other scenarios, the kind of questions that we can expect to get in our exam. Let's say we would be possibly asked some kind of questions like this. Let's say 1 molar concentrations of sodium chloride. Let's say we have got 10 molar concentrations of, or we better take 1 molar each. So we have, let's say, 1 molar glucose, we have 1 molar barium chloride, and we have 1 molar potassium hexacyanoferrate. Okay, so what we see is, the question is, which one has the highest boiling point, okay, or which one will have the highest elevation in the boiling point. So highest elevation in boiling point, let's say. So what we can see is, the 1 molar of sodium chloride, sodium will break apart into sodium ion and chloride ion, so we can have 2 times increase in the concentration. So technically 1 molar NaCl will be 2 molar. Okay, like the glucose, it will remain as one single entity, so its concentration doesn't change, so it will remain 1 molar. Barium chloride, barium will break apart into 1 barium ion and 2 chloride ion. It means the concentration of barium will increase by how many times? By 3 times. So 1 molar would become 3 molar. Okay, exactly like that, we'll have 4 times potassium ion and 1 times hexacyanoferrate ion. Okay, 1 time. So 1 and 4, our concentration, that means, would increase by how many times? By 5 times. And the elevation of boiling point, the elevation in boiling point, this is nothing but a qualitative property. Okay, and we understand that qualitative property is directly proportional to concentration. Okay, so that means the one with the highest concentration would have the highest elevation in boiling point. So since 5 molar concentration is the highest out here, so that means 5 molar concentration of this solution, or we can say 1 molar K4FeCN6, will have the highest elevation in boiling point. Okay, that is one possible question that could be asked in our entrance exams. We need to take care of it. And if we take related with this, we may also possibly get some other questions like this. Instead of the elevation in boiling point, instead of this, they could possibly ask us which of the following will have the lowest depression of freezing point, or they could possibly ask us which one would have the maximum lowering of vapor pressure, or which one would have the highest increase of osmotic pressure. In all the cases, since these are qualitative properties, they are directly going to be proportional with the concentrations. So that means in any of these choices, if they would have given it to us, okay, either for this particular question or for this or for this, okay, our answer would still be 1 molar K4FeCN6, because it dissociates to produce the highest number of the ions. So if it dissociates to produce 5 times the ion, our concentration would increase by 5 molar, so that means it would have the highest qualitative property. So I hope it's clear with everyone. Thank you.